Hi everyone, I'm PrachiGupta. Welcome to the Collab 8, the linear algebra for deep learning. Today we are going to master the mathematical language that powers the entire field of deep learning. We have got an exciting roadmap. Uh, we will start with building basic blocks like scalars, vectors, move through matrix transformations. Eventually, we'll see how complex concepts derive complex systems like transformers, PCA, all those things. So you wonder why we do need maths at all, right? So here's the magic. It's all about the speed. Instead of processing one piece of data at a time, linear algebra allows us to process massive batches in parallel. It's difference between slow one by one calculation, the lightning fast processing of modern GPUs. So that's why we use the linear algebra. Now let's first we'll see how it works. First we will import all the required files. I'll just run it. Once the required files are imported, we'll print the version. Once we are done with this, we'll see the code. So yeah, this is done. Let's move ahead. So as we have already seen that while doing the batch processing, we do x at the rate w is equals to y. Why we do it? Because it's the matrix operation. It is matrix multiplication, which is much faster than normal calculation, which is a normal dot product. That's why we use it. So let's see how a single neuron works mathematically. Let's ground this in reality. Think of this code for a single neuron as the fundamental building block of every neural network. We have inputs like pixels, pixel values, weights, which the network learns, and the bias shifts the output. So the input, weights, and the bias. So I'll just run it. Just give me a second. So we are here. See, single neuron computation inputs, weights, and bias. We'll multiply the input with weights and then we will add the bias. So, this is how the calculation is done. Now, the magic happens right here. If you see, the magic happens right here in the weighted sum. This is the dot product, a single line of code that represents the heartbeat of an artificial intelligence. So, here we do the np dot dot. This is the main thing which do the whole concept. Now think of the dot product as a measure of alignment. If input and weight vectors point the same direction, if you get a strong activation, if you get a strong activation, if there are if they are perpendicular, the activation is weak. This simple geometric alignment is how neuron decides to fire. So if we see, we will plot it, and I'll just run it. So you see, we are plotting inputs, the weights, and weight dot sum plus biases. So this is the large positive. The vector points in the same direction. The strong the activations are. If we have the large negative and vector points opposite direction, the strong negative activation we will have. So what is the next we are going to see? Uh, we are going to see the fundamental operations of deep learning. We will now systematically build up linear algebra knowledge like scalars, vector, matrices, and the transfers, and then the operations and their property, what we can do on them and what is the special characteristics of them in the deep learning. And these are the building blocks. So we have scalar, single number, vector, a list of numbers, matrix, a table of numbers, transfers, multidimensional, 0D to 1D, 2D, 3D. So let's start with the scalar. Scalar is just a single number in the deep learning. Scalar represents the learning rate, loss value, regularization strength, all these single values. So let's see the code. So I'll just run it. We have the scalars. These are zero dimensional, just single numbers. Think of this as knobs of your network, like learning rate or the final loss value. Now we have vector, one dimensional. These are 1D list. In practice, a vector might be a list of features or embeddings. Visually they are points or the directions in the space, and if we visualize them, they are the points or the directions in the space. A key insight here in the deep learning is similar data points will have the vectors that point similar direction. So this is the main point here. Now moving towards the 2D matrices, this is where we move from individual logic to industrial scale processing. A matrix can represent a layer's weight and a whole batch data. When we calculate x at the rate w, we are transforming an entire batch of data in one go. So I'll just run this matrices code. If you see, uh, we have this weight matrix, we have this batch sample, we do x at the rate w, and this is what we get as output. So this is what we get as output. Now we will plot it. So we can see the heat map, where it shows the weight matrix, the input batch x, and when we do the product, what comes is the output. So matrix multiplication transform entire batch at once. Instead of doing one by one, it transforms the entire batch at once, and this is why GPUs are essential for the optimization of matrix. Finally, we reach the tensors, the generalization of these shapes to 3D and higher. For NLP, we use 3D tensors to handle the batches of text. For computer vision, we use 4D tensors to represent the batches of color images. Deep learning is really just the art of tensor transformation. So let's see how do we introduce tensor. So here in the code we have this random tensor numpy array we have created, and then we are printing the shape, and then we are again having one numpy random integer image random array, and then we will print the shape and the details. So this is the random what we have created. Again, this is one more random. So now we will plot it. So yeah, this is a 3D tensor visualization, how it looks in 3D. Deep learning is all about tensor transformations. We give input tensors, layers through layers, output tensor, and layers through prediction. So this is the basic flow. Now, if you look at the shapes used in, so let me just, so we have this. If you look at the shapes used in the models like resonate or BERT, you will notice a pattern. The first dimension is almost always the batch size. This is exactly what enables a massive parallel processing we talked about. Let me just run it. So if you see, this is input after flatten and the output. For ImageNet also it's the same. For text classification it's the same. For language model it's the same. So first dimension, if you see, it's 64, 64, 64. For ResNet it's 32, 32, 32. For text classification is 16, 16, 16. For language GPT 888. So the first dimension is almost always the batch size that enables parallel processing for multiple samples. Moving forward, we'll see the section 1 is completed. We'll see the vectors now. Now that we have our blocks, let's see how we move them. We rely on four key operation: addition, scalar multiplication, the dot product, and the Hadamard product. So that is element wise product. So let's move forward. Addition of the vectors are same as we have seen in the numpy. Moving forward, we have plotted graph also for that. So vector addition powers residual connections in network like ResNet. By adding the input back to the output, we allow gradients to flow directly through the network and solving the vanishing gradient problem. Moving towards the is a multiplication. Scalar multiplication is our primary tool for optimization during the gradient descent. We multiply our gradients by a small scalar, the learning rate to make precise, controlled, and adjustment to our weights. So let me just run it. We can see the vector, the scalar. If we multiply zero point 0.5 with all this, our output turns like this. Just give me a second. So this is how multiplication works. Now moving towards the dot product is our heavy lifter. Beyond neuron activation, we can use it for cosine similarity to see how closely related two embeddings are. It's how a model knows that king and queen are similar concept. So let me just run this. It's step by step details. We can see A and B are matrix. Step by step we'll multiply and then add the product. So using dot operator, using at the rate, using multiplication, all gives the same output only. So moving forward, um, we are just plotting the details. So let me run the cell and you can see the dot product, cosine similarity, everything is plotted here. The dot product measures alignment between the vectors, same direction positive, perpendicular 0, and opposite direction negative. So this is the alignment we can interpret from the graph. Moving forward, deep learning application in cosine similarity word embedding. We have already discussed this cosine similarities. Element wise operation. So finally the Hadamard product. This is element wise multiplication. Think of it like a gate. In an LSTM, the forget gate is uses the operations to decide exactly which piece of memory to keep and which to discard by multiplying the memory by a vector of zeros and ones. So let's see. So we have this two elements and we do a multiplication operator and we'll print it and let's see how the output looks like. So I'll just run it. So it will be 5 into 1 will be 5, 6 into 2 12, 7 into 3 21, 8 into 4 32. So this is A dot B and each position is this. So this is how we define it. Now our section 2 is completed and let's move forward to the matrix operations. Uh, as we move to layers, we transition to matrix vector multiplication. You can think of this as a sequence of dot products. Each output neuron in a layer is actually just the result of dot product between the input and one row of the weight matrix. So let me just run it and let's see. So if A is equals to this and B is equals to this, the simply addition is the addition of the addresses, like 00 adds to 00, 01 adds to 01. Similarly all the addition happens and that's all for the matrix addition. For matrix to vector multiplication, we have a single vector and if we multiply it to the matrix, how it looks, let's see in the output. So we have this vector, we have this vector, we have this matrix. If we multiply it to the vector, where the output will look something like this. It is basically the product of this to this dot product. It is the dot product of this row to this row. It is the dot product of same vector to this row, and this is the results that we store. So this is how the matrix multiplication works. Now Now here is the golden rule of matrix multiplication for a at the rate b to work. Those inner dimension must match. My favorite memory trick: the inner dimension disappears and the outer dimension remain to define your result. So how do we see it? If I run this code, we can see it. So this is the weight of matrix. This is the input vector, and this is our output vector looks. So this is all about the matrix multiplication. Now look at this batch processing in action. We are processing four samples at once. So matrix multiplication is core operation in the neural network. It enables the batch processing, layer transformation, efficient computation. So if you look here, um, multi just matrix multiplication we have already done. So just so this is the same matrix multiplication that we have already done. We'll move toward the batch processing. So look at this batch processing in action. We are processing four sample at once. While CPU might do these things one by one, GPU does all this multiplication in parallel. This efficiency is why matrix multiplication is the heart of deep learning. So if you run it, we have this three random numpy arrays, matrices, and then we are doing this computation. So all this computation is done once, and this is how we get the output. So we processed all the four samples in once, and that's what we discussed. Beyond basic operation, matrices have a special property that are essential for advanced network mechanics. So first we plot this. We are done with the batch processing. Now we will see the special matrix properties, that is transpose, inverse, and determinant. Transpose is basically flip the rows and the columns. The rows become columns and the column become rows. To do this, we just have to do a dot t, so it will transpose the matrix. So if you run it, you can see 1 2 3 4 5 6 will become 1 4 2 5 and 3 6. Now next is this. I'll run it. So the transpose where we flip the rows and the column, it's critical because you will see it everywhere in the attention mechanism. We can calculate the scores using q at the rate k. We can calculate the scores using attention score using k at the rate k. It's also the engine for back propagation, allowing gradients to flow back through the weights. So if you run this, it is the attention scores, and this is it is calculated by q at the rate t k kt. So now matrix inverse. So matrix inverse are the rare in practical coding because they are too expensive to compute. Instead of undoing the transformation with an inverse, we use optimization algorithms to find our solution. So if you see, if you want to inverse it, we will do a at the rate a inverse, and to inverse it, we will do np lin alg dot inv inverse. So if you multiply the matrix with its inverse, you will get a identity matrix. So let me just run it, and this is the output. Now the next is determinant. uh, Determinants are the determinants basically tells us how a matrix scales space. A determinant of 4 means the area of quadrupled. If the determinant is negative, the orient flips. If it's 0, the matrix is singular. If it has squared, singular. If the matrix is singular, it has squashed the data in the lower dimension, and the information is lost for forever. So these are the some basic rules. Now let's try running it. So what we are doing is we are defining plots, we are defining an array, and then we are doing the determinant part here. Determinant 4, the area multiplies by 4. Determinant is 1, so the area is preserved, just the shape changes. So determinant, if greater then the area will be multiplied. If determinant is 1, the area will be preserved, only the shape is changing. And here if the determinant is 0, it collapses. So this is how it works. Now next is eigenvalues and the eigenvectors. So let's look at the soul of a matrix, that is eigenvalues and eigenvectors. There are special directions that does not change their orientation when a transformation is applied. They only get scaled. So let us see how. So this is our eigenvalues calculation. So we have a matrix and we have a eigenvalue, and we have this eigenvector columns. So how do we get it? We have a np dot array eigenvalues and eigenvectors is equals to np lin alg dot eig will give us the eigenvalues and the eigenvectors. Once we get this, we will print the eigenvalues and the eigenvector, and we have this formula where a at the rate v is equals to lambda at the rate v, where v is the eigenvector and lambda is the eigenvalue. So once we have these values, eigenvector and the eigen vector, we will calculate it and we will print it out. So both are equal, so the formula is proved. We'll also run this. So the section 6 is completed. The norms and distances we have already seen in earlier video, so we'll just move forward. And our section 7 is completed. So this is the summary of what we have gone through, and this is the core equation of deep learning. Y is equals to activation of x at the rate w plus b, and where x are the input, y weight and bias and the output. And this is a complete neural network forward pass code. If you go through it, you will understand it. It's basically very simple. We have samples, input, hidden layers and the outputs. We have defined our weight, bias, weight 2, bias 2. We have this input batch random. We'll compute this network. We'll calculate the linear transformation and the ReLU activation, and then we will, after layer 1, we will compute our details, and again we'll do it for the layer 2, and we will apply the softmax function and we'll print the details. So you can see the output. This is the input. After layer 1, we will see the ReLU and the output. After layer 2, we are seeing the output, and this is the predicted class. So that's it. Every neural network is just matrix multiplication, bias addition and an activation function. That's it. So that's all for this video. Thank you so much.